persevere. Okay, so I want to clarify one point. And so I have a coordinate frame like this, and I talk about a rotation about angle theta around an axis, right? We have to follow the right-hand rule, right, to define our positive rotation. So we align our thumb along the axis that we want to rotate about. Make your fingers point in the next axis. So for x1, our fingers are going to point to x2. For rotating about x2, our fingers point to x3. And then close your fingers, and you'll see we have a rotation like this. That's our positive theta direction. And from that, we can write our coordinate transformation matrix as cosine theta, sine theta, minus sine theta, cosine theta. Okay? Now, I did put up, for extra reading in case anyone needed it, from Macy Chapter 2, which is the Mathematical Fundamentals. A couple of the examples there do the coordinate transformation wrong. So be very careful about that. As far as I can tell, in chapters 3 and 4, the reading that I actually assigned, the transformations are done correctly. Just the examples in this mathematical preliminaries chapter that I put up just for extra reading so people would have it are wrong. So please take note of that. So then we did a couple problems in groups. And the first one is this delta rosette, and it's for measuring a strain gauge. And each one of these measures a stretch or a compression in one direction, right? And so if we're doing with plane strain here, so we have no out of plane components. We've got a strain tensor that looks like this. We only measure one component directly. Right? The other two components, we have to calculate what they are from these other two strain gauges. So we can create, let's make another axis here, x1 prime, and we'll make another axis here, x1 double prime. This strain here is 4 times 10 to the minus 4, and this one is 2 times 10 to the minus 4. All right. So what we have to do is, we know this is 60 degrees. This is 120 degrees because this is an equilateral triangle. So our theta to x prime is 60. Our theta to x double prime is 120 degrees. So that means our Q from x to x prime is cosine 60 sine 60 minus sine 120 cosine of 120. All right. Okay. Now, Q for x double prime is going to be cosine 120. Horrors. Okay. I screwed up all this. I wrote that completely wrong. Q for x prime, the angle is 60. I was thinking ahead to the next one. And I did it again. Okay. So, what we want to do is we want to write epsilon prime and epsilon double prime in terms of epsilon, and then we can solve for our missing components. So what we have is epsilon prime equals q x prime epsilon q x prime transpose. Right? And if we do that, we get epsilon 1 1 prime is equal to minus 3 plus epsilon 2 2 by 2 plus minus 3 minus epsilon 2 2 by 2 times minus 1 half plus epsilon 1 2 by 2 square root of 3 over 2. And if we do epsilon double prime is qx double prime epsilon qx double prime transpose, we get epsilon double prime, that's equal to 4 times 10. Yeah, that's equal to 4. I'm just scaling everything by 10 to the minus 4. I get minus 3 plus epsilon 2 2 by 2 plus minus minus 3 minus epsilon 2 2 by 2 times minus 1 half minus epsilon 1 2 by 2 square root of 3 over 2 equals 2. Right? And what we end up with is epsilon 2 2 equals 5. And epsilon 1 2, we can solve these two, equals 4 over the square root of 3. So our strain tensor then becomes minus 3, 5, 4 over the square root of 3, 4 over the square root of 3, times 10 to the minus 4. All right, that's our strain tensor. Well, I'm afraid I'm going to screw it up again, so I'm just going to redraw it. Right, here's our cube right? Our length here is dl, right? And this was labeled ABGH, right? And I said the body diagonal AG. I labeled this backwards. GH. So for our body diagonal GH, that vector, right, that's dx, in our undeformed frame, has 0 and x, but dly and dl and z, right? So that's what our vector looks like. And if we do now 0 dl times 2 times our strain tensor, 0, 0, 0, 0, 0, k squared 2k, 2k, k squared, 0 dl, right? Remember, this is dx dot 2e dot dx, right? And this is equal to the length squared in the deformed minus the length squared in the reference, right? And that gives us 2k plus k squared dl squared, right? And that'll be exactly the same for the other body diagonal, right? You end up with a difference. For BH, the difference goes to, you have a minus 2k here, right? That's how BH changes, right? So then there were a couple homework questions. So 3.3, you're given a stress tensor, I'm sorry, where we're missing a term. The problem we want to find is we want to determine the normal vector to the plane that is stress-free. Okay? So what this is asking us to do is find if sigma n is equal to our traction vector. This is asking us to find the n so that we have that we're traction free. So n1, n2, n3 equals 0, 0, 0. And obviously we're not interested in the trivial solution of n1, n2, n3 equals 0. So if we multiply this out, we have sigma 1, 1, n1 plus 2, n2 plus n3 equals 0. n1 equals minus n3. n1 equals minus 2n2. So that gives us that we can solve this for sigma 1, 1, and we get sigma 1, 1 equals 2. Right? We can now plug this back in, solve for n's, right? Remember, we always have the condition that n1 squared plus n2 squared plus 3 squared equals 1. So that gives us enough equations. Alternatively, in MATLAB, you can find we're interested in finding the null space of this stress tensor. If you remember your linear algebra. All right. And then there was a question on 3.9. Okay. So the question was the curved cylinder surface. Well, so we're given this stress tensor. Right? So we have AX2 plus BX3 CX3 minus CX2 CX3 0 0 0 0 minus CX2. So the first part says verify that equilibrium conditions are satisfied, right, in the absence of body forces. So we're just going to, in that case, just evaluate the stress, right? Take your derivatives, and make sure that holds. The second part of it, where the question was, it says show that the stress vector vanishes at all points on the curved surface of the cylinder. So we got a cylinder here with radius r, and this is x2, x3, and x1 is coming out at us. So what is the equation of this curved surface? Well, it's just a circle, right? So it's x2 squared plus x3 squared equals r squared, or x2 squared plus x3 squared minus r squared equals 0, right? And then we want the normal vector to the surface, right? So we take our gradient. Right? And so from there, we're going to take the gradient right, with respect to x2, and then with respect to x3. So we get 0, 2x2, 2x3. Right? That's the normal vector. If we're at a point on this on this cylinder, this curved surface, this will give us the normal vector at any point that's on the surface. Okay? And then question 310, there was also a question about. I'm going to pause this just for a second. Hold on. Okay, I think we're back recording. So for problem 310, part 1, the rotation. So here the problem says we're rotating about the 111 vector, right, or the 111 crystallographic vector. And for 120 degrees, that's pretty easy because x1 goes to x2, x2 goes to x3, and x3 goes to x1. Then it says, well, what about 60 degrees? And you can either do a lot of trig, you can draw it out and take all your cosines, but there's a shortcut called the Rodriguez rotation formula. Right? And what it's for the it's actually more advanced than what we need here. But so we have if v is the vector we want to rotate, right? And k is the axis of rotation. K is by definition a unit vector. So in our case, v is going to be our coordinate axes, x1, x2, and x3. K is going to be our 1, 1, 1 direction. And what the Rodriguez formula says, that v prime, our rotated, is equal to v cosine of the angle plus k cross v sine of the angle plus k times k dot v 1 minus the cosine of the angle. Now we can write that a little more compactly in matrix notation by using something that's called the Crossproduct matrix. But what we can do is we can write, this is our rotation matrix R, which is equal to the transpose of our coordinate transformation matrix. All right, this is identity plus sine of the angle right, where K is this cross product matrix. Right, and it comes up. You can read about it. Go to the Wikipedia page as to exactly how this is defined. But oops, it's an anti-symmetric matrix. Right, and this matrix has the property that whatever you multiply it by, right, it's the same as so k little k cross v equals k v. So it's this matrix. This matrix encodes the cross product. Right, and that will give you a rotation matrix for the axes, but we're interested in coordinate transformation. So we have to take the transpose of it. So in this case, we get, if you work it out for the three axes, we get Q equals 2/3, 2/3, minus 1/3, minus 1/3, 2/3, 2/3, 2/3, minus 1/3, 2/3. So check and make sure that that's the Q that you get. And then sigma prime is just Q sigma Q transpose. Okay, that's all we got for today. So thanks, and I'll try and get an actual in-class recording for Wednesday.